Okay, I wanted to talk about this formula for expected value. If we just look over here, E brackets X, what does that mean? It means the expected value of our discrete random variables. And remember that those variables are just numbers, right? So if I had some values and their associated probabilities, so the probability that X, the variable, equals that particular value, I don't know, half of the time we get 0, a quarter of the time we get 1, and let's say another quarter of the time we get 2, right? Using this formula, I can work out a theoretical mean very easily by simply saying we need to sum. From here we've got the first value through to the third value. And that would look like this. We'd have 0 times a half plus 1 times a quarter plus 2 times a quarter. So we'd end up with 1 quarter plus 2 quarters is 3 quarters, right? So based on those probabilities, the expected value, right, notice that it doesn't equal one of these particular values. It's an average. We'd expect it to fall at 3 quarters. And that's how you use the formula. But I really want to talk about where does the formula come from. Just before we start though, a word about this symbol mu. Sometimes used to represent population mean as opposed to a sample mean. Right, so sample mean, we get this symbol, sample mean. I want you to think about it really, the mu, as a theoretical mean. Okay, and in that way, the theoretical mean and the expected value are effectively the same. Okay. But to derive the formula, I would actually like to look at an experiment. So the experiment, I will make it up. The experiment is going to be rolling a die. And I'm doing this to try and connect it to your prior knowledge of probability. So imagine we're rolling a die. What could our values be? 1, 2, 3, 4, 5, and 6. And let's think up some frequencies for these values. Okay. So frequencies, maybe I get 4 1s, maybe I get 6 2s, 3 3s, I don't know, 5 4s. We could have, I don't know, 7 and maybe just 1 6. Right. Now, the probability normally would be 1/6. There'd be a 1/6 chance that we could get a 1, 2, 3, 4, 5, 6. But if we actually did an experiment, we might get some quite different answers. The total number of rolls here, that's really important for probability. You need to always know what your n is, or what your frequency is out of. What is the total here? We've got 8 plus 8 is 16 plus 4. We've got 26 as our total. Total frequency. And we could look at relative frequencies. Relative frequency, which is effectively like the experimental probability, right? So 4 out of 26 of the times I rolled a 1. 6 out of 26 of the times I rolled a 2, and so on. Let's try and do this quickly. 7 out of 26 I got a 5. Only 1 out of the 26 rolls did I get a 6. All right, so this relative frequency, we can think about that as our experimental probabilities. Experimental. So I've done the experiment. Experimental probabilities, right? Okay, now let's say I wanted to work out the average, right, or the mean. This is experimental mean or sample mean, so I'm going to use this symbol. Well, I'd have to add up all 26 of the results. 1 plus 1 plus 1, there were 4 of those, there were 6 2s plus 2, and so on, and so on, and so on, and so on, until I got up to the last value, which would be a 6, and then I divide it all by 26. So to show this using symbols, I could say, well, I've done the first value plus the second value plus the third value plus all the way up to the nth value, and I've divided by n. So n is what's it out of. N is the total frequency. N is the total number of numbers, or the number of experiments that I've done. But there'd be a shortcut way to do this mean, which hopefully you've seen before. I could do this instead. I could say, well, I had 4 ones. So I could say I had 4 ones, and I had 6 2s, and I had 3 3s, and so on, up till the last one, which is I had 1 6, and I divide all that by 26. Okay, so I'm still working out a sample mean. I could say this sample means come from, like the first frequency times the first value, plus the second frequency times the second value, and so on until I got up to the 6th frequency and the 6th value, and I divided it all by the n. Okay. So what would that mean for us in this experiment? It would mean doing, I've already done it up here. All right. Let's look at what we've done here, because I can rewrite this slightly differently. Right? 4 out of 26 of the time times that first value 1. I could add up all the numbers, then divide by 26, or I could write it like this: 4 on 26 times the number 1 plus 6 out of 26 of the times I got a 2 plus 3 out of 26 of the times I got a 3, up until the last one that I did, which is only 1 out of 26 times the 6. Okay, and can you see that when I write it as these as a fraction, they're the same as the experimental probability, right? There's the 4 out of 26, there's the 6 out of 26, right? And that's because the experimental probability, or a probability, can be thought of as a frequency divided by n, right? So if I knew the frequency and I knew the n, I could get to the mean without having it to do it the long way and add up all 26 of my outcomes and then divide them by n at the end. Using the experimental probabilities or the relative frequency, this has already been done for me in a sense, right? And that's where this formula here comes in. All right, so this probability here already includes the dividing by n, and it's taken into account the frequency of each value. Okay, it's a little bit if you just thought of a really simple average, like say I wanted to get the mean of some numbers, I don't know, 3, 4, and 9, okay? So what would I have to do? I'd have to say 3 plus 4 plus 9 divided by 3 numbers, right? N equals 3 there. But I could write these values in a table. So there was a 3, there was a 4, there was a 9. One third of the values was a 3, 1/3 was a 4, 1/3 was a 9. And so I could use a slightly different method. It's really all the same thing. Plus third of 9. Now, what is this? It's 16 on 3. So you could see the same thing here. We've got this common denominator, and we get the same answer. All right. Now, this formula, when we're applying it, is giving us an expected value. Right? Hopefully you're now convinced that this formula will calculate means. I've done it with an experiment. Right? But the expected value, I want you to think of as being theoretical mean in most instances. Now, just look at the book. They use a spinner here. Right? So for an experiment or when the mean is theoretical, the mean that you get will not be exactly the same as one of the values. Well, it could be, but it probably won't be. Looking at this spinner, so going to the book's example, they've got these values. 5, 10, 15, and 50. And the probability that the variable will equal that value is 1/4 for each of them. And that's because we have an equally weighted spinner cut up into quarters. Right? To work out the expected value, they've already done it here, so I won't redo it. But the expected value of our variables would be 1/4 times 50. They've started at this end for some reason. 1 plus 1/4 times 15. Right? And that's how we're using this formula that we've got up the top. Right? So we need to do the value times the probability. Do that for the first one. 1/4 times 5 plus, right? Remember this is a sum, plus 10 times 1/4 plus 1/4 times 15 plus 1/4 times 50. All right, in this case it's 20. So how would we interpret that result? It means that on average, right, if I kept spinning this over and over and over, on average, I would expect those values to average out to be 20. Okay. You can see in this speech bubble, you're not actually going to get 20 on any spin, but we would expect the average to equal 20, right? Okay, I'll leave it there, I think. Hopefully you can appreciate this nice simple formula and where it comes from, and it's really quite simple to use, which is good news for us because it makes calculating these theoretical means or expected values fairly straightforward.